Hello, and today we are going through proofs, which is week 28 of the math map. And the first thing that Dr. Gilpin showed in book club was for the quick flip arithmetic to do a distributive property, but where you have two quantities that have two terms to them, so they're polynomials, and then your, like if you had something like, x minus 10, and then you had x plus 3. So those quantities are each going to be polynomials because they have two terms, and then it's still distributive property, but you FOIL, that's how I learned it in high school. So you do your first terms, so that'd be x squared. You do your outside terms, so I'm doing FOIL. First terms together, and then you do your outside terms, so that's 3 times x, so 3x. Inside terms, which is what the I stands for, that would be minus 10x. And then your last terms. So that's the negative 10 times 3, which is negative 30. And then you combine like terms. So you have positive 3x and negative 10x. So that's going to get you to negative 7x. And these stay the same. And then you can't simplify that anymore. So she shows that for the quick flip arithmetic. And it is distributive property, so instead of having just one term over here that we distribute to this whole quantity, we're distributing a polynomial quantity to a polynomial quantity. Personally, I feel like that's something you're going to do in algebra. You're probably going to do it in polynomials. You'll do it in your freshman year of high school. I don't feel like my kids were ready to do this and to understand this. They're barely understanding the distributive property and taking the one term and multiplying it by the quantity. I'm happy when they can figure that out. So I didn't even bother doing this with my class because my class personally, I didn't feel like they could handle this and work on this, and it was just going to be deer in the headlights. So instead, I decided to do something maybe that is kind of a little different, and you may or may not want to do it because it may not be what you think works for your class. Okay, so what I decided to do, and if you download my lesson plan from the director's page, you'll see that I have, it says Euclid Elements, Proposition 1. So Euclid, who was the famous Greek, philosopher, he's more of a mathematician. He's kind of known as the father of geometry. So he put together 13 volumes of books of proofs, pretty much, that prove different things in geometry. So he's looking at triangles and shapes and lines and how things all tie together. And so, and if you really wanted to be classical, you could look at his books and go through them and work through your understanding of geometry just from looking at his books, not even using a textbook. So that's like ultra classical to do something like that. But I thought it would be fun for our kids to see what one of those proofs look like. And I went with Proposition 1, the first proof, because I think it was a simple enough one that the kids could all kind of see and follow along. And what I actually did is that last page, I typed it up for you guys. And so it's the last page of the lesson plans. And I actually printed it out and gave one to each student so they could follow along and they could take it home and kind of see how proofs are constructed. So it says Proposition 1 for Euclid's Elements, this is in book 1, on a given finite straight line, to construct an equilateral triangle. So we're going to make an equilateral triangle. All three sides will be the same length. And we're doing that by just starting with a line, a straight line, finite straight line, meaning that it has endpoints. Finite does not go on forever, right? It's finite. It's not infinite. And they'll probably understand that because we've been discussing those things. So we're going to say, let AB be the given finite straight line. Thus, it is required to construct an equilateral triangle on a straight line AB with the center AB and the distance, or the center A and the distance AB that will make a circle BCD as described. And so to make that circle, and I already packed my compass, so this is probably not going to be as beautiful of a circle as I could have made. It turned out okay at class, so I don't know. I managed to keep my pencil the right size. So you're going to, if you have a compass and you can put your dry erase marker on one side, you're just going to use your compass. Oh man, to make a circle. Okay. This turned out a lot better in class, I promise. But, and we're going to have some points on that circle, but I'm not labeling them yet because I don't have them drawn. But we are going to have circle B, C, and D. And so D is kind of like over here. And then again, with B being the center point, you're going to use your compass and measure that same length. And it says with center B and distance BA, let the circle ACE be described. Okay? And so how we do that one is you're just doing it the opposite direction. Okay, so B is your center, A is over here. Oh, and the dogs are going crazy because somebody's at the front door. Oh, okay, that turned out horrible, but trust me, the real one looks a lot better. Okay, and so what it says is that with center point C, let the circles cut one another. This is their cut point to the point A and B, and so this becomes point C. And so this circle was ACE, and this circle was BCD, and that's what he mentions. So let the straight lines CA, you could get out a ruler and draw that, and CB be joined. Wow, so now since the point A is the center of CBD, AC is equal to AB. And since the center point B is the center of the circle ACE, then that means that BC is equal to BA. So these lengths are all the same length. It is an equilateral triangle. And so you did that because you started with that finite straight line and it allowed you to make the circles, and then you were able to create an equilateral triangle. And so you're proving the construction of this, of how you can make the triangle. And the very last line of this says, therefore, and if you want to remind the students, remember our symbol for therefore? It's these three little dots in a triangle shape. Therefore, the three straight lines, CA, AB, BC, are equal to one another. They're all equal, and you can mark it like that, and that's how we know those sides are all equal. Therefore, the triangle ABC is equilateral and has been constructed on a given finite straight line of AB. And the very last line says, being what it was required to do. That last line is kind of your summation of, here is my proof. I just finished it. I demonstrated it. This was the proof of what I was trying to show you. And we're going to kind of learn the term for that and what you in modern day kind of use as your last statement on your proof to show that you are at the end of your proof. Therefore, I just demonstrated and proved my proof. Okay, so that was just kind of an introduction to what a proof looks like. What do these things actually look like? We're not going to be asking the kids to make full proofs at this point in time, but I wanted them to have an understanding of what is this thing that we're talking about. Okay, so that is what I did for my warm-up for the kids. We spent about 5 minutes generating this, kind of looking over how it looks on the sheet, and then we jumped into Math Map like we normally do. Okay, so the next thing I did is I just said, check out your compass page, tell me where we are, and they can look down on complex, week 28. We're still in ND, we're still in the imagination space. And then I asked them, what dimension has been your favorite? Which dimension did you guys like this year? And they all had some ideas on what they liked for various reasons. One of the artists said that they like 3D because it's so much more exciting when you take that 2D and you're trying to shade it and do all this stuff to make it look like a 3D item. Somebody else said they really like 2D because they could see all the graphs, they could see how stuff goes together. Somebody else said 1D because it's just so simple and exact. And then somebody else said fourth dimension because wow, it's just amazing to think about all this stuff through space and switching out time and going through time. So it was just kind of cool to have a little bit of conversation about what did they like for the different dimensions and see that they had an understanding of what those different dimensions are. So that's pretty cool. Then the other thing we did is moved on to the exordium. So looking at the cover, and then I said, okay, so this is what you're seeing right here is actually part of a larger mural that's on the wall at the Vatican. And there's a bigger painting and all of it is titled The School at Athens. So we're in Athens, Greece. And there's a big thing with a bunch of different stuff going on at the School of Athens. And this was painted by Raphael. but we're just seeing a photograph of one section of that mural. So that's what we're seeing here. And then I said, what do you guys see? And they could tell that we had ancient Greeks, because we also kind of just discussed that. And they said, and he's dealing with a compass and he's showing them geometry. And so that was awesome that they could pick out on that. And then they noticed that there were some spheres over here. And they're like, one of them kind of looks like the world. And then one of them, I said, maybe the other one could be like stars, like an idea of what the constellations are like. So that was kind of neat. And then I pointed out that when Raphael painted this, he actually used one of his other artist friends as his model to make Euclid. So this is meant to be Euclid right here in the center, teaching the others with the geometry. And we just saw one of Euclid's proofs. So that's kind of cool to tie it together. And then I said, and then his other buddy, Leonardo da Vinci, apparently posed as the image for Plato. But I don't know who Plato is supposed to be, because I've only seen pictures of Leonardo da Vinci when he's an old man. So I don't know what he looked like when he was younger. But they were guessing that maybe Plato is in the green. I don't know if somebody out there knows which one is supposed to represent Plato. Put it in the comments so the directors in the future years will know who it is who's representing Plato. But that was kind of cool to see that and see what they're noticing. Then I read through the quote. And it mentions in the quote how mathematical knowledge has a greater certainty than any other. And let me see what some of my notes are on this. So, I noted that we don't always think in a logical way, right? As individuals, this was mentioned in the conversation topics or whatever on the back of that first page, that in a letter to a friend, Emily Dickinson wrote these words: "The heart wants what it wants." And some of the girls in my class go, "Oh, no, Selena Gomez sang that." And I'm like, no, she was not the first. That's actually from Emily Dickinson, who was a poet. And so the heart wants what it wants, because we don't always think logically, and we think emotionally, we think with our hearts. We're not led by logic and truth all the time, but that math works in absolutes. And so math is absolute. 1 + 1 is going to equal 2. And sometimes people further their studies, and sometimes you go into English and you're in college and you have a professor who doesn't like your opinion on something, so they mark up all your paper just because they don't like your opinion, not because your writing was bad. But the beautiful thing with math is that math is math, and it's absolute. If you have that right answer, you have completed the right answer. So there's not a lot of like wiggle room and opinion on it, which can appeal to a lot of people who like that kind of absolute. And then we read through the reflection, and then I said, any other thoughts on how it ties to proofs? Every time I ask that question, they usually don't have any other thoughts, but I ask it anyway because we're supposed to. Okay, then the next page is to go through our I2 invention page. And so I started it by saying, what do you know about proof? What does it mean when I say, give me proof? And so some of the kids chimed up that, well, in a legal courtroom, you'd have to have proof or evidence for something. And I said, yeah, perfect. So you have your legal evidence, your proof. If somebody they think maybe somebody's guilty, or they're on trial for being guilty, and they have some proof or some evidence, does that mean with absolute certainty that person is guilty just because you might have a few pieces of evidence? And they said, no, you can't have 100% certainty, right? Especially if you don't have a confession or anything. You don't know absolutely. And I said, right. So in a legal standpoint, you don't have 100% proof. How about in science? And some of them realized, well, you make a hypothesis like we did in science fair, and you have to make your study so that other people can do your study and keep trying to get the same results. And I said, and that gives further support for your hypothesis. But is science ever proving anything 100%? No, it can get a very good accuracy, and it can say over and over again, the studies have shown this, the scientific community accepts this, but it can't say 100% absolute proof. But on the other hand, mathematical proof is something that we always know. It is absolute. And then the other thing I said, is God's truth absolute as well? And they said yes. So good, they were able to kind of figure that all out. Then the next thing we did is go into the common topics for that invention page. So first common topic, compare statement and reasons. And so, where did my thing go? So on here, they have on the bottom part under the 2-column proof, it says statements are given over here, and then the reasons are mentioned over on this side, over here. And they'll see a few examples of that in the student pages. Then define the terms by reading the definitions. So there's terms on the top of this page, and then definitions. We didn't go through all these definitions yet, but I worked through the first student page, which is pretty much that upper part is the same as the upper part of the first page. So they'll go through those definitions in some detail when we get to that part. So I didn't go through it here because this had more info and I didn't want to spend too much time on it. But under my circumstance, for my next common topic, what are the circumstances for the different styles of proof? And so I showed how, sorry, we've packed up our bookshelf, so I have nothing to set my stuff down already. Okay, there are 4 proofs that we go through in the math map. There are more proofs out there, but these are the 4 that math map is choosing to focus on that a high schooler would tackle and look at. So they don't go through all types, they just go through these 4 types. And so let's talk about what those 4 types mean in just a little bit more detail. So the first one that we have is proof by construction. They're all going to have proof by in their wording. So I'm just going to write that down here. Proof by construction. And so this is proving how something came to be. So you're kind of building up your evidence, or you're building up your reasoning as to how something came to be. So you basically build a model, you build up something that satisfies the conditions. So if I asked you, does 2 + 2 = 4, or prove that 2 + 2 = 4, you might build up other arguments. Integers are whole numbers, and each time you add a whole number, you're adding 1 more to the numbers. Rules of addition, when you're adding things together, you combine them. So when you're combining the 2 + 2 as whole number integers, you get to 4. So something like that. That's a really simple example, but proof by construction is building up something to prove something else that's generally accepted. Okay, proof by contraposition. So proof by contraposition. Okay, so this is kind of more your logical argument. So I lifted my coffee cup in class and I said, a good cup of coffee has creamer in it. If coffee doesn't have creamer in it, then it's not a good cup of coffee. So that's kind of an example. So you're using logical arguments, and then if something doesn't have that, then it does not follow the logical argument. You can't get to the same conclusion. Proof by contradiction is the next one. Contradiction. Okay, so this is the idea that the opposite of whatever you're doing is impossible. Therefore, what you're doing must be possible because the opposite is not possible. Okay, so therefore this has to be true. So that's all we said for this. And then I reminded him that therefore is symbolized by just these 3 little dots. And then the last proof that we talk about is proof by induction. And so this is the idea of numbers and patterns kind of helping be your proof. So if I said to you, 2, 4, 6, 8, what's the next number? And they all guessed 10. And I said, and what's the rule? How did you get to that? And they would say, well, each one of them was adding 2. I'd say, yes. So if I asked you to prove it, you would just show how you added 2 each time and you got to the same answer. So that would be proof by induction. So there we go, a little bit of a step into those 4 proofs. Then back to our common topics, discuss the relationship between the proof and the given. So given are the facts or assumptions that are accepted as true. So it's something that you already accept. Whole numbers, as you add together, will increase and join together. The proof is the larger logical argument that demonstrates the truth of the statement. And then last part of 5 common topics, authority. So discuss which part of the proof is a statement of authority. And so the reasons or the statements become authority. The other thing that you see is what we saw at the end of our Euclid proof, or similar to that. You might see QED, which stands for the Latin, it's quod erat, right? Oh, let me look it up. I think it's quod erat demonstratum. Okay, and I didn't write it down in my notes. Quod erat demonstratum. We'll see it in the definition on the kids page, the first page. And so basically this is what was demonstrated, that which was demonstrated. So that which was demonstrated, it's just the Latin, and they abbreviate it by just having the first letters. So quod erat demonstratum, that which was demonstrated. So that's basically at the end of the Euclid one where he says, because it is accepted, it was written so, or something like that. This is just how we'll see it now in modern day. Okay, the next thing we do is we go to our Memoria and arrangement page, which looks like this. You have a lot of triangles, shapes. So what would be helpful to kind of memorize and look at? Well, we talked about some of those definitions. So you see how on the left side you have AA, and then you have SSS. So those are, the A stands for angle, S stands for side. A little bit lower down here, you have an H for hypotenuse, L for the leg of the triangle. So those are abbreviations they might see for geometry. And then they're just comparing different things. On here, let's see, it says the arrangement. So things that are similar, this upper box is showing you the triangles that are similar. So they might have they would have the same angles, but maybe their sizing gets larger. So this triangle has the same angle type thing as this one, it's just a larger version of it. Or this one maybe is rotated, or it's just comparing that they're the same. This one is flipped, it's like rotated over that plane, vertical plane. So it's just a way of saying how are they similar. Now congruent is what we have down here. Congruent have to be the same size. And so they are referred to congruent corresponding size. They have to be the same size. They still are related. So we can see we have similar sides that are similar, but that one's flipped, and each triangle is still the same size. So these are congruent, these are similar. That's probably the big thing for them to focus in on for that. Now, in terms of the charts, this is usually where we highlight kind of what are the main topics or what are the main things that we want them to get out of this week. And the first one is the purpose of proof. So in legal or scientific definitions, we use proof to try to support something, but it still has uncertainty. We talked about that. But in mathematics, things are always true. So we have absolute truths. And then the other concept to introduce to them this week is inductive versus deductive reasoning. And I'm going to write those out because I wrote this on the board for my students as well, so they would see how it's spelled. They can kind of start putting it into their brains, what these things mean. And so we had inductive and we had deductive. Okay, so inductive reasoning requires experience. Okay, so this is the toddler that sees that the stove is red, something is red, the stove is on, and they touch it and they burn their hand and they pull back. And then maybe later they see that the stove is red again and they touch it and oh, it's still hot and it still burned my hand. And through that they learn, okay, when stove is red, stove is hot, hot burns my hand and it hurts. And then they don't touch it anymore. Okay, so that was reasoning, inductive reasoning. Deductive reasoning is the toddler hearing their mom say, honey, I turned the stove on and the stove is going to get hot. Don't touch it, else it's going to burn you. And the toddler doesn't even have to touch it. They say, you know what? My mom tells me the truth. My mom told me this is going to be hot and it would burn me. So I know it will burn me even though I didn't have to touch it to understand that. That's deductive reasoning. So I know something to be true, therefore something else must be true. I know mom tells me the truth, and so then therefore this must mean that the stove will be hot and burn me if I touch it. So that's more like proof by construction or contraposition or contradiction. And then inductive reasoning, where you had to go through the pattern and go through the experience, that's more like inductive proof by induction. Okay, so there you go, the different proofs. the next thing that I did, I always say, do you want to go through anything from last week? They never do, but that's the time when I ask them about it. And then for the first student page, we went through that together as a group. And I will show you what that first student page looks like. Okay, so see how on the top, you're going through the definition? So I read the definition, and then they shouted out as a class which of the items on the left matched the definition. And the only one that they missed, there was a little confusion between given and axiom. So the axiom and the given, and we just had defined that earlier, so that's why there was a little confusion. But all the others they quickly got, and they were able to understand, which was awesome. And then this lower part on this proof by construction, I drew those two linear lines. Let me put down my, okay, I went ahead and I drew these two lines, and I labeled the lines, and I wrote the numbers in here, and I reminded them, okay, when we have a straight line and we're looking at this angle and this angle, they have to add together to what? What do we have when we have a straight line? Those two angles would have to add to 180 degrees because it's half of a circle, and a full circle all the way around would be 360 degrees. But we have this half gets to, so the measure of angle 4 and the measure of angle 1 equals to 180 degrees. And then you do the same thing. 4 and 3 would add together to 180 degrees. Measures for angles 3 and 2 would total to 180 degrees. And 2 and 1 will also total to 180 degrees. So they had a chance to kind of see how that all works out. And then down here, we're just comparing the measure of the angles. And so where they compare, now the ones that say, that don't have measure in front of it, it's just saying the angle, those ones are not correlated. And then over on here, they're just adding angles together. So if I tell you this one angle is so many degrees, then you know the 3 has to be so many degrees. And if you were adding them together, you could total that and figure out what it is. So we went through and totaled these together as a whole class. Then I divided them into their teams of 2, and they worked through pages 2, 3, and 4 of the student pages. And what I did in class is what I do most weeks, and I wrote this out, not the stuff where they're not solving anything because it's just too much to write it all, but I wrote this little image, and I just had this thing about congruent means this, and then the vertical angles, the corresponding, and the alternate interior angles. So I wrote that up on the board, and then they come in once they're done solving it. I give them like 5 to 10 minutes. Once they're done working on it with their partner, they come up and they fill in all the stuff on the board with the correct answers. So they did that. And then the second group had the right triangle. So they had a proof about right triangles that they worked on. And they actually finished that so quickly that they went ahead and solved the rest of the page, which was awesome. And then the third group had maybe a little bit harder one, but we had some different angles, and they had to kind of match it together and see how that all fit together. So it was a fun lesson. They were excited to get to try to do some stuff with proof. I asked them if any of their older siblings are in high school that are working on proofs at all, and nobody thought that they had been. So I thought that was interesting that maybe they're even tackling a math concept their other junior and senior siblings were not doing yet. Okay, so I think that is all. Oh, and then I reminded them that next week is Seeing the Unseen, which are their week 29 booklets. And then I said, have you guys been working on those? And a couple of them were like, oh, I had a lot of stuff early on, and then I haven't really done anything. And I said, you might want to fill in some more stuff for that because you never know what we're going to do next week. So you might want to make sure that you have some things written down. So anytime you've seen math in the world, or you've witnessed God in mathematics, so tie that stuff together, jot some of your notes, draw some pictures, however you want to do it, but try to put some stuff in those booklets because you're bringing them next week. And I'm going to have some sort of prize for the student who has the most stuff completed. They don't know that though. But that's one of my benefits to the kid that bothered to keep working on it throughout the year is here you go, I have some prizes for you. Okay, so I think that was all for proofs, and I'm not sure we'll have a point for a video next week, but maybe I'll just go through a bunch of examples of what people had in their Seeing the Unseen booklets. I think I've shown mine, or at least part of mine, but I'll show you my full booklet of what I've put in there, and we'll see what some of the kids have done, and hopefully that'll be helpful too. Thanks for watching.